Hello everyone, welcome to another round of video. This is based on the topic capacitance. We'll just introduce the topic and then say one or two things about it, just for you guys to have an idea of what it actually does. Alright, capacitors are actually the electrical devices used to store energy in electric circuits, commonly for a backup release of energy if the power fails. So it's more like it tends to provide the support. It's not the main source of power, but it's actually like a backup. It's actually like a backup. It's got two metal plates, like you can see in the diagram on the screen. It's got two metal plates. Um, we've got a dielectric in between those plates. When we say dielectric, we're talking about substances that the power conductors of electricity, but they've got a good supporter of electric fields. Now, what that does is it actually helps the charges. It makes sure that the charges does not flow freely between the plates. You've got the positive charge connection, you've got the negative charge connections, you've got the metal plates, the dielectric, the aluminium, and the plastic insulation, just for the storage of the energy in the place. All right, and then we can talk about the what we call the capacitance, which is more like a term we use when we're talking about the charge stored per unit potential difference between the plates, and it's got the symbol which you have right on the screen. And then the capacitors usually have a rating. You've got 35 volts, 1000 microfarads. Now for a capacitor, the more the capacitance, the greater the energy that that capacitor can store. And we have right on the screen 1 farad is like the standard, but then for we're talking about 1 farad is actually a very large unit. So in calculations, what you tend to find is microfarads, nanofarads, and sometimes picofarads. Okay, it's just perhaps capacitors just need like a minimum store of energy that can get things running if the main source of power fails. Let's go right into the equation. All right, we've got C equals Q over V. The C is the capacitor measured in farads. We've got the Q, that's the charge measured in coulombs. We've got the V, that's potential difference. That's the energy transferred per unit of charge flowing from one point to the other. All right, and now this equation is more like a standard when you're working with calculations and all of that stuff. All right, now the Q you've got in this equation is not actually the charge of the capacitor itself. It's actually the charge stored on those plates. Yeah, for still on the capacitance equation, it's more like the ratio of the charge stored by the capacitor, the plates on the capacitor, to the potential difference. So it's more like a comparison. All right, now we've got a question here. It says a parallel plate capacitor has a capacitance of 1 nanofarads and is connected to a voltage supply of 0.3 kilovolts. Calculate the charge on the plates. First things first, nanofarads is 10 raised to the power of minus 9. So you've got to convert that to farads. So when you're working with capacitance, capacitors, the calculations, you've got to change the unit, whether you give it in, if it's microfarads, that's 10 raised to the power of minus 6. If it's nanofarads, 10 raised to the power of minus 9. That's very important. If you don't do that, then you can mess up your calculations real bad. Right, now we've got the potential difference given in the question. That's 0.3 kilovolts. Now kilovolts is really a large store of energy, and the standard for potential difference is volts. So you've got to multiply that by 100. 1000 This is what we've got there. And then we have what we've been given. Another equation that connects all those together. We've got C, capacitance equals the charge stored by the capacitor over the potential difference. And then we go ahead to rearrange this, guys, because we're asked to calculate the charge. That's what the question says. Calculate the charge on the plates. So we plug in our values. After rearranging, we plug in our values. We go 1 times 10 raised to the power of minus 9 times 0.3 times 10 raised to the power of 3, and that gives you 3 times 10 raised to the power of minus 7 coulombs as your charge. Charge is measured in coulombs, and then you can tone that down to about 300 nanocoulombs. All right, so that will be all for this video.